Okay, so thanks, Ariel. So my name is Chris Markiewicz. I work at the Stanford Center for Reproducible Neuroscience, and I'm the maintainer for NiBabel, or NiBabel or NiBabel, depending on how you want to do it. One of the nice things about Babel is that it's all about not being able to understand each other, so we can all just call it however we want. So today, that's what I'm going to be talking about. And so NiBabel is a Python library for manipulating neuroimaging data structures. So I think that's about what I'm about to say here. Yeah. So NiBabel low-level Python library gives access to. Oh, actually, before we get going, I just want to say this is a slideshow version of the notebook that you should be seeing in Jupyter Lab. So if you go to curriculum, NiBabel, open up NiBabel. I'm not sure actually if it's going to get upset with me for having multiple versions open. So this is what you should be seeing. This works just as a normal Jupyter notebook, but if I go up here and I change this to tree, so if you want to watch it as a slideshow on your own side, then you can also do this. So tree, curriculum, then come in here, and then you open this up. Let me go ahead and close this just to show you what it looks like. We're in a normal Jupyter notebook, and then there's a little graph thing here. So you can open that, and we're back in this slideshow. So feel free to follow along however you want. Okay. There we go. Sorry, I need to move me so that I can see my slides. Okay, so the idea of NiBabel is to basically have a one-stop shop for reading and writing pretty much any neuroimaging data that you're likely to come across. It's obviously a work in progress. There are formats that aren't supported yet, but we do support quite a number of them, including both Nifty1 and Nifty2, MGH, which is a free surfer format, Mink 1 and 2, AFNIS, BrickHead, multiple versions of Analyze, DICOM, PARREC, ECAT, and these are all basically the same kind of image. They tend to be these volumetric images. We also have surface file formats such as GIFTY and various free surfer structures. And then we also have support for tractography files and SIFTY2, which is a kind of odd format. It's neither surface nor volume, but a bit of both, and sometimes neither. So I'll talk about that a bit more later as well. So to get going, if you don't, you'll have this installed on the Jupyter Hub, but if you just need to get NiBabel, you install it with pip install, or if you're on Conda, if you're using Conda, you can install with Conda Forge. Yes, and we'll be using NiBabel 3, which requires Python 3.5 or newer. I assume most people are going to be able to do that, but if you're stuck using Python 2.7, there's going to be some features in this presentation that you aren't going to be able to access. So just to get through the basics, you import NiBabel, and basically there are two common ways to import it that I've seen as NB or as NIB. I'm using NB here. I've seen other slideshows or other presentations this week where they use nib instead of NB. So, do what you like. Ideally, use the same convention throughout a project though. This is just a number of useful imports. I'm not really going to go through them, except for when you see NLP, that means I'm using NiLearn. Wait, that actually did make sense. Okay, it's a NiLearn plotting. NDI is SciPy's n-dimensional image. NumPy, which I assume you guys have seen, is NP. That's most of it. And then I wrote this data. Oh, in case you're not familiar with this pathlib notion, it's just a nice interface for how to write paths instead of doing everything as strings. I'm assuming there aren't already questions. Oh, there is one already. I guess I will do that really quickly. So where are we supposed to install it? In your Python environment, when you're ready to start a new project. Yeah, I'm not sure if this was really gone over in a previous discussion of where to install.
I'm wondering sort of if the question here is where we install NiBabel in general, or if we're supposed to install it right now as we're running this. It's installed on the hub. So if you're running this if you're looking at the hub right now, it's there already. More generally, going over sort of how to install software is maybe out of scope for this particular presentation, but we can add a little bit of documentation to the materials that talks about how to install all the various things.
Yeah.
I hope that answers that question.
Yeah. So yes, there's that was just supposed to be demonstrative in case you're working in a different environment. Right now, that's not something that we need to work on here. So hopefully, I'm sorry if I give any confusion there. Okay, so what do we want to cover in this talk? So this is actually going to cover from really basics to somewhat advanced usage in NiBabel. So I hope that whatever your familiarity with NiBabel is, that you'll get something out of it. It's if you've never used it before, you will learn some things. If you've used, unless you're extremely fluent in it, you will probably still learn something. So that's my goal. So the first thing we want to be able to do is just load and save different types of files in NiBabel, figure out how to get data in and out of Python objects. Then what I'm going to spend probably half of this lecture really talking about the spatial image API. How do we deal with volumetric images, and what are some of the tricks that NiBabel has for dealing with memory problems, because neuroimaging data can actually get quite large. Ideally, you don't have to use a supercomputer to do everything. Okay, and then other things. So kind of on the same line of that is we want to discuss this difference between array and proxy images, which that might be more of a 2A subheading. And then I also am going to go over some surface image formats, SIFT2 files, and the tractography API. So let's get going. The basic input-output features, loading. So the way I would almost always recommend loading an image is just nibabel.load. And recalling that datadir was a path object, we add to the path just by using / and putting in the rest of the path. NiBabel will support that, but it will also support strings. So, oh, right, I actually did not run these previous things. Let me go back and run them. Okay. Okay, so we load that. We could also just as easily say string. And I guess let me just show you what that looks like. Oh, well, I think when I print it, it turns it into a string anyway, so never mind. But just so you, or no, that's how these paths work. Okay, so let's keep going. And when we just look at the image itself, we see it tells you what type of image it is. It gives you some information about the shape. It shows you the affine, which I will get into. And it shows you all of the fields in the header. And I'll get into that later as well. But that just gives you, that's a quick way to look at an image and get a sense of what you're doing. Saving, my recommendation is almost always to take the image and use the toFileName method. And so here we're going to just save to the temporary directory. But there is also the sort of complement to nibabel.load is nibabel.save. But one thing that this tries to do for you is if I give it an extension that doesn't match the file type I'm using, so I have a nifty, if I give it an MGZ file, it will go ahead and convert that for me. We might lose some data if there's some mismatch between the two image types. And that's part of why I recommend using toFileName is if I try to do this with an MGZ, it's just going to yell at me because that doesn't look right. So then I'll have some kind of warning that my save attempt is failing in some way. Okay, so another thing you can do with the save is, so Nifty has both a single file type, which is .nii, and it can also be image header pairs. And if you save to an image.image file, then it will automatically create image.header to go with it. Same file name, different path, and then I can load either of those and get the original image back. So just heads up on that. The other way to get data in and out of NiBabel is to use the to bytes and from bytes methods. So this is most images that go to a single file. If you just use image.2bytes, you will get a byte string, and that just looks like that. And so this is exactly what would be on the file if you wrote it to file, but this is something that you might want if you need to, say, send your image over a network and don't want to save it to a file, send the file, and then open the file somewhere else. You can write your code a little bit more cleanly. And so on the other side, you would somehow get your hands on this byte string, and then in this case, you would actually have to know that it's a Nifty 1 image. There isn't a generic load from bytes method, at least not yet. So here I would say from bytes, and I get this new T1, and I can print that as well and demonstrate that it is in fact what you'd expect. Okay. And so images that save to single files can generally be serialized. Nifty 1 and 2, Gifty and MGH are supported. Sifty 2 is actually supported as well, but not until the next release. That's a oversight that I discovered while making this presentation. Okay, so now let's talk about spatial images. So when you get your data off of the scanner, it's almost always going to be a 3D, maybe 4D array of basically a picture of the brain and possibly multiple time points. So you might end up with a 4D array. So you can do an awful lot in this type of format. And so most tools will let you operate with volumes. And so there are a lot of different files or file types that different tools use, usually to contain some metadata that's useful for their context. So usually you get your image off as a DICOM, and then you'll probably convert it to Nifty or maybe Mink or MGH if you're in the free surfer world. You might use Brickhead if you're in the AFNI world. And all of these have basically the same structure. So that you have the data array, which is the data that you actually recorded. You'll have an affine matrix, which provides a spatial interpretation of the data. And then you have metadata, which, as I sort of discussed, is, if you get it off a DICOM, it's going to have a lot of patient information. If you're looking at a Nifty, it's going to have various things that Nifty has encoded in the header. And so the API that to access these is just, if you look at your data, you use .getFdata. You can access the affine. It was just the affine property, and the header as the header property. So the reason that the getF data looks a little bit different is that NiBabel tries to keep data on disk until you actually need it. So getF data reflects that you're doing some work. You're pulling the data off of the hard drive. But sometimes all you really need to know is some information about the data array without looking at it directly. So for instance, you can look at how many dimensions does it have, or how many shape, or what is its shape, by just looking. And these are exposed directly through the image itself, because we can tell that what the data is going to look like before loading it. So sometimes we can save ourselves time. So let's look at the data array. Actually, are there questions now? Let's see, I think I see one. Could you elaborate more on the byte string? What is it used for? Yeah, so the byte string is, so if you're working just with images and your goal is to, your goal is to load an image, modify it in some way, or read something out of it and save some result, as another file, then the byte string isn't going to be very useful for you. But say you have written a web app that will load an image, extract some, or modify it somewhere, and then ship it off to some server you have in order to maybe archive it or do some more extensive processing. The easy way to do that is to encode it directly as a byte string and send it along a network stream. And then on the other side, your server will accept a byte string, and then it needs to know how to turn that back into a NiBabel image, assuming that it's written in Python, in order to operate it with it in a coherent fashion. So hopefully that was, oh, sorry, the controls on this are a little bit annoying. Okay, so let me see, did I answer that question? What was the oversight I mentioned? Oh, the oversight was simply that the SIFT-E2 images to and from bytes didn't work up until about a week ago, and that hasn't been released yet. Okay, is there another Q&A? Does using a byte string make it more efficient? Not particularly, though it does depend on what you're doing. If you don't want to deal with your hard drive, then yes, it can be more efficient because you don't have the disk IO as an operation. But I don't see, it's more about what you're trying to do. It's not a stunningly efficient process. For instance, it doesn't get gzip, so the size of it the size of the byte string is the size of the uncompressed NIFTU. But yeah, I mean, if you're sending something over the network, you can always gzip the stream as well. Okay, I'm gonna move on. Okay, so the data array, as I mentioned, this is just a basic NumPy array. So you can do things like look at its shape. And so what I'm doing here is I'm finding the central slices in each dimension. So I have the data shape that tells me how long it is in each dimension. I create that as a NumPy array and divide it by 2 using integer division to ensure that I get an actual index as opposed to some possible 0.5. And so then the main thing to look at here is I'm slicing the data object. So I'm taking the middle slice in the first dimension, the middle slice in the second dimension, and the middle slice in the third dimension. And that's just a quick way that I can have a look at the image and see what does it look like a brain. It does look like a brain, which is great. I don't know that it's worth my going into the subplotting issue. It's just a quick way of showing 3 images next to each other. Okay, so each location in the image data array is a voxel, which is a pixel with a volume or a volumetric pixel. I'm not sure if everybody's familiar with that terminology, but that's what we refer to those cubes inside a data array as. And they can be referred to with voxel coordinates, which just means the indices in the array. So this is a useful way to look at the data, but if I want to say, where in the brain is this? If I want to give you coordinates that would be useful to, say, a neurosurgeon, it's almost entirely useless. So what we need to talk about is, yeah, actually, I was skipping a slide in my mind. Okay, so we can do some things automatically here with using the information that's in the image. So if you use image.orthoview, it will scale it up so that if any of your voxels are, say, wider in one dimension than another, things will start looking a bit more human instead of squashed with this method, because it will scale the voxels to their sizes that are declared in the header. It also will label your orientations, so posterior, anterior, inferior, superior, left, and right. And this green crosshair is pointing at some origin. And this origin is in what we call a world space, or maybe a reference space. And the idea of that is, if I want to say this is so many millimeters to the right or left, it's right or left of what? It's right or left of this origin. So things on the right hemisphere generally are going to have a coordinate that's positive in the first space. and then on the left hemisphere, it'll be negative. So how does this even happen? This is all encoded in this 16 parameter array called the affine matrix, and that's what I'll be getting into now. So some basic terminology. So an affine transform, it's a matrix. So we're doing some basic linear algebra. And so we're trying to describe the transformation from voxel space to this reference space. And again, voxel space is just the index. So 0, 0, 0 in voxel space is just the corner. 0, 0, 0 in reference space is some center, however defined. And that definition, of course, is through the affine. And so we can calculate it just through simple matrix multiplication. And the matrix has this form. So there's a 3 by 3 you can sort of think of it as a slope matrix, and then a 3 by 1 intercept matrix. And by adding in this row of zeros and ones and adding the ones to the bottom of these coordinates, we allow this all to be done as a single matrix operation as opposed to a matrix multiplication followed by an addition. Okay, so what are these? Oh yes, so the goal of this affine is to tell us what right and left are, what anterior, posterior are, what superior, inferior are. And so positive in the right-left direction, or positive in the first coordinate is right-left, so more right than left. Positive in the second is more anterior than posterior. Positive in the third is more superior than inferior. And these are defined in the scanner by what would it look like if, from the subject's perspective, lying face up in the scanner. And so just to be very clear on this, we refer to this as RAS plus space, which means as you move positive, you're moving right, anterior, and superior. Some people have previously used RAS to refer to starting at the right, anterior, superior end, which would be the exact opposite for us. So trying to be very explicit about all of our assumptions. So here's an image of what this looks like. So you're looking at a reference scan that you often take as the first thing in the scanner, and then you decide I want to set the bounding box for, say, my structural image is I want to capture the whole brain, but for my bold image, maybe I only care about some areas of the brain more than others for reasons of speed. And so you might you might have different shapes of image, and they all have to have some way to refer to one another. Okay, I feel like we're probably going to get into questions soon, but let's go on since I don't see any. So the affine is probably best thought of as a series of transformations. So if we look in this image, we have this black box, which is a representation of the voxels. So moving one unit in here is moving one in the voxel space. So if you think of it as you scale, rotate, and translate, then the first thing you do is you scale up so that the voxels are the size of a meaningful size relative to the actual brain. So we say these are, maybe these are 3 millimeter voxels, so we scale by 3. And then we rotate so that the brain is in the same space. And then we translate so that they're in, so that the center of the image is in its intended location. So there's a tool out there called Transforms 3D, which allows you to decompose an affine matrix. And this is getting a little bit into the weeds, but to try to give you a little bit of intuition, we can say it's a translation, a rotation, a scaling or a zoom, and a shear. So translation is just a shift, rotation is a rotation in space, scaling is scaling up or down, saying your voxels are larger or smaller than 1 millimeter, and shear is basically how far, so each voxel is a 3-dimensional object. If it's a perfect cube, or if it's a perfect rectangular prism, it'll have 0 shear. If it's slightly off, so one of the sides is a parallelogram, then it will have a non-zero shear. Okay, so we can look at our T1 affine. And so we see we have translation parameters, we have a rotation matrix, we have our zooms, so our voxel size, we see we have about 1 millimeter, 1.3 millimeters, and 1 millimeter. And there is a little bit of shear, and here I'm using the maximum absolute value, but it's 10 to the minus 6, so it's pretty minimal. And just to demonstrate that this is actually a valid decomposition and it's applied from right to left, I decided to reconstruct the affine matrix. And that how you're reconstructing it doesn't really matter so much as the fact that we have a translation matrix, a rotation matrix, a zoom matrix, and a shear matrix. And if we apply them in this order, and at here, I'm not sure, I assume you went over this in NumPy. At is just matrix multiplication. So it's the same as if you saw the other form, you would have seen tm dot rm dot zm dot sn. And so we end up getting or reconstructing the affine matrix from that. Okay, I see a question that's probably appropriate. Why is it named decompose 4.4? Yes, so there is a generic decomposition, and then there's an optimized one for 4x4 matrices. So there, you could also use decompose, and you should get like to within floating point rounding error, the identical results. Okay, so you have an affine matrix. That's the rough idea of what it's doing. What can we do with it as a programmer? So we can extract some information from it. So we can just directly ask it, what orientation is this image in? This image happens to be in the RAS space. So there's not a significant rotation so that we would worry that, you know, the subject would be like facing to the left, for instance. Orientation and code. So increasing along an axis moves to the right or left, the axis is encoded RL. And so that uses the af-to-ax codes operation. We can also fetch the zooms or scaling factor directly from the affine using the affine's voxel sizes. And there's also a measure of obliquity, which is a kind of weird concept, but basically tries to say how far if the matrix is pointing, if the subject is facing directly ahead. So when it says anterior, you're actually looking directly anterior of the subject, then it will have zero obliquity there. But a lot of the times the subject's head is slightly tilted in the scanner. And so obliquity gives you a measure of how is it tilted left, right, along each of the three principal axes. And it's also, you know, a basic linear algebra object. So you can use it directly to answer questions that NiBabel doesn't provide for a tool to do. So for instance, we can say, I know that I want to find the the voxel coordinates of the center of the image. So there's that 0, 0, 0 coordinate, and I want to find what voxel is that inside. So for that, what I would do is I would invert the matrix, because of course the matrix is telling us how to go from voxels to world coordinates. If we want to go the other way, we just simply use the inverse. And then we use 0, 0, 0 as the coordinate. And then of course you have to, you have to put in this 1 in order to make the linear algebra work. If you don't do that, you're going to have problems. But then we get out of that, the ijk, and this will end up being a 1. So I just use underscore to indicate that I'm not interested in it. And so I can show you that the center is inside the voxel at 126 voxels in, or 127 voxels into the first axis, 66 in the second, and 172 on the left, because we're zero indexing. And we can actually look at the value at that location. Okay. Can I clarify the difference between voxel and world coordinates? Right. Let me go up a couple slides to cover that. So yeah, I'm not sure that it's a little bit of a wonky idea, and I'm not sure I have the best images for it. So the voxel coordinates is just what index in the voxel array is it? And it's purely a way of talking about where am I in a block of memory, which has no anatomical meaning. So the world coordinates are a set of coordinates in millimeters, right anterior and superior of some center that is defined in usually roughly in the middle of the image. And the affine matrix tells you how to get between those. And so in a sense, the affine matrix defines what the world coordinates are. But those are particular to any given image. So if you want to say talk about, if you want to talk between images, then you have to do something called registration, which is to find the difference by some method of these two world coordinates, and then you either keep track of that adjustment or you just change the affine of one of your images, so that when I talk about the same world coordinate in these two different images, it may be a different voxel coordinate, but I'm still talking about the same place in the brain. So I hope that was an answer to your question there. Okay. Yeah. So that's all to say that this is kind of in detail stuff, and if you didn't follow all of that, that's fine. So the two important points I would say is that affines provide a spatial interpretation of the data, and you mostly you need to keep track of, you need to be aware enough of it to keep track of it. So if you go and make a new image, you can't just give it the data array. You have to give it the affine that has the correct spatial interpretation, or otherwise your new image is unusable. And also that occasionally you might want to extract some information from the affine, and NiBabel has some tools for working with it. I think Noah is going to go over this in more detail later today. And there's also in the NiBabel documentation, there's a coordinate systems and affines tutorial that goes into much greater detail, and I can't recommend it enough. Okay, so now let's move on to the third part of the spatial image. Remember, we had the data array and we had the affine matrix, and now we just have the image header. So most of the time, similar to the affine, you're actually not going to care a whole great deal about this. So the main purpose a header has is to contain enough information to construct the data in affine arrays, because remember, well, I'm not sure how many are familiar with how data is stored on disk, but it's just one long string. And so knowing how far along that string do I go before I cut to a new row in my array, and how many rows do I go before I cut to a new column in the array, is all important information. And so the affine is also encoded there somewhere. A couple things that are useful is we can fetch the zooms or the scaling factors from the image without even looking at the affine. Sometimes it's encoded directly in the header. And if your data is 4-dimensional, then this will be the fourth zoom will be a temporal one, which will correspond to repetition time. So, or at least in the bold fMRI context, it'll be repetition time. In other contexts, it may have another interpretation. Okay, and the other thing that you might not care about, but you should be aware of, is the data D type. And this is something that trips people up. So the data D type tells you what is the type of the data when it's stored on the disk. It is not necessarily the type of the data that you want to work with. And this is also, so if it's also the type that when you save the image, it'll be there. So if you've changed your data type and you really need it to be a float, you might want to change the D type. And we'll get into more about that later, because otherwise what's going to happen is it will coerce your data into this D type, possibly with scaling, and save it, and that might not be what you intend. Okay. So for images with, oh, I see questions in case. Oh, I think those were already answered. Okay. So for images like NIfty and MGH, they're a fairly common type of binary header, which is just field after field, and they have types, and they're defined somewhere in usually a C header file. And so they're extremely straightforward to just look at. You tell NumPy what this stretch of data has this interpretation. So we might have an integer, we might have a byte array, we might have an array of integers, or we might have an array of floating point numbers. And so all of these are accessible just by saying header and then treating it like a dictionary. So if I want to find the description field here, I can just ask header description. Other types of headers may not have this interface, so it's something you need to know a little bit about which type of image you're looking at. So yes, here show MGH. So if you guys remember, I saved the image.mgz earlier, so we can just load that and print the header. It has a very similar format, but you can see that the data inside it is quite different. I can still ask for a header field that's there, and my get zooms and get data D type are still valid things that I can do, because that's part of the image, the header API. Okay, so other formats, pargrec and brichead, for instance, use text key value pairs. So they have a different interface for accessing these. The Mink files are also use separate container formats that have their own methods for fetching metadata. Yes, so again, often we're not necessarily interested in the header for its own sake, but if we're creating a new image and we're not changing it substantially from the input image, it's often a good idea to copy the original header in to preserve any useful information that is there. So just to get to that, we'll create an image. So the usual way, at least for me, that I will perform some kind of operation on an image is I will fetch the data, and this will be a rich data. Oh, right. So this will be the original data, and then I'll perform some operation on that data to get new data, and then I will just return a new image with the new data and the old affine and the old header. So the new data, this image.class. If you haven't run across this before, this is just a way of saying I want to get the same type of image out as I put in. If I wanted to say specifically that I want this to be a nifty1 image, then I would put in the nifty1 image class. But this is a shorthand that allows me to write something that doesn't really care about what type of image I get in. So if I get a MGH image in, then this function will spit an MGH image out. If I set nifty1 image, then I put in an MGH image, I get a nifty1 image out, and I may lose some header information as a result. But sometimes you do need that, sometimes you even need to assume that, because you might want to modify a header field that only exists in Nifty because you want to record something about what you've done. So you have to choose a little bit carefully about that. So here's an example. Say we want to fetch we want to rescale our entire image into a single unsigned byte, because we just want to look at it. We don't care about any fluctuation that is smaller than 1/256th of the total range of the data. So the way to do that is, here's a simple rescaling function. We subtract the minimum, multiply it, or divide it by the range to get a value between 0 and 1, multiply it by 255. So now we have a value between 0 and 255. Cast that to a unsigned byte, so an 8-bit integer. And then we create our new image. Now here because we've created this image and it's uint8, our input image may not have that data type. In fact, almost certainly doesn't if we're bothering to do this. So if we want to actually see the savings on disk space, then we would need to set the data type to uint8 to be sure that the image goes out the way we expect it to. So we can rescale an image and then put it or save it to this file name. Okay, so it's been about 45 minutes. I wonder if we should take maybe a 5-minute break in case, because this next bit's going to be a little involved.
That sounds good. Let's take 5 minutes here and come back.
Okay, so we'll come back at 10 minutes to the hour. Okay, I think I suppose people are probably back. Maybe one more minute.
Yeah, give folks one more minute until we hit 7:50 on my clock, and we'll get
Okay.
started again. Okay, I think you can get going again.
Sounds good. Okay, so next thing I'm going to talk about is we're going to go into more detail on the data object, basically. So if I create a new image from scratch, so here I would use NiBabel nifty image, and then I'm just going to create a 2x3x4 array with these values, and I'll just give it an affine saying there's a zoom of 2. I'm not going to really worry about translation or anything like that. Okay, so if I actually look at the data object, which is that's saved as the data object, and this is how you access it. So I see the original data that I put in. Now, if I save this image and I load it, then now instead of looking at, or when I look at the data object, instead of it being just an array, it is now an array proxy object. So what is that? It is an object that knows how to access the data, but it doesn't do so until you request it in some way. So the obvious way to request the data is with get fdata, which is a method that always gives you a floating point data type back. And we'll get into a little bit later why it's always floating point. But just for now, that you should know that you can always get a floating point representation, which means you can operate on it with confidence that you're not going to run into any int float differences in how things behave. You can also set the data type. So it provides a very predictable interface, but sometimes you want more control over it. Sometimes a floating point representation isn't appropriate. So in those cases, you're going to want to work with the array proxy directly. And so how do you do that? The basic idea of an array proxy is that it's supposed to act as much as possible like a NumPy array without loading all the data. So the easy way to say, I just want this array, give me the data or whatever it looks like, is use numpy.asAnyArray. And the nice thing about asAnyArray as opposed to asArray or array is it will work really hard not to copy it unless it has to. So if you have an uncompressed image, it can pull up a memory map that is just directly looks at the data on disk without loading it into memory at all. And again, this is only possible with uncompressed images. So another thing you can do with the image array is if you know that you want it in a particular data type, you can always say, you can just cast it. So uint8, I want a unsigned character version of this data object. Now this is potentially dangerous, and I constructed this array specifically to show this. If you remember that this value here is 256, if you cast to a uint8, then it just lops off that first byte and shows you a 0. So you effectively get a modular division by 256 on all of this. You can also cast it up to an insanely large complex data type. And so this gives you the flexibility to choose what you want to do. So for instance, if you know you have a label image, you might want to say, give me this as an integer. Maybe the labels are coming from some tool that encodes them as int16. So you say, okay, give this to me as an int16. Don't bother, even if somebody went and encoded it as a larger data type, don't bother giving that to me. Another way you can access this data, instead of taking the whole array, is you can index it or you can slice it. So this indexing and slicing works exactly the way it does on a NumPy array, but it will only read the data from disk that you request, so that it can be a lot faster. So if I just want, say, the first, if I want to take so okay, I want to take the first sagittal slice of the image, then I might say data object 0, and I'll get back the sagittal slice as a 2D array. Maybe I want to take some of the slices along the inferior superior direction, and so I can use a 1:3 slice. And I'm not sure if you guys have seen this dot dot dot. It's called an ellipsis, and it allows you to avoid writing a bunch of colons that you don't have to. So the other way to write this for a 3D array would be colon, colon. But if I don't know whether I have a 3D array or a 4D array, if I have a 4D array, what I might want it to do is that. And a dot 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 will insert as many as needed to make sure that I have, or that I'm actually selecting the final axis. Okay, so this is useful for if I want to take the first volume from a bold series. I can take volume 0, the bold data object, and I'll skip all of the spatial dimensions and just grab the first instance of the fourth dimension. So all of this does work with both uncompressed and compressed data. If you want a free speed up for pretty much anything you're writing where you use nifty GZs, install the index gzip package as part of your dependencies for your tool, and you get basically loading the whole data object is almost as fast as loading it from an uncompressed image, and the same thing is true for slicing parts of it. Okay, so what else are there questions on that before I don't see any? Okay, so what else does the array proxy do? One thing it does is it allows you to have your data as one data type on disk and still work with it as a floating point of the correct interpretation. Okay, let me back up and start that again. So nifty files have a slope and an intercept. These are called scaling factors. That allows me to do something like say I'm going to encode this data in this data range, but I actually want to represent this data. I want the range of that to be twice what I'm saying. So I might put a slope of 2, or maybe my intercept is 500. That just means I add 500 to all of the values. And so when I request data from an array proxy, it will do that transparently. And so that allows us to extend the data range or precision beyond the on-disk type. So probably the most common situation that I see this in is that a lot of images, especially when they come off the scanner, are encoded as int16 or uint16, because that's a larger type than the scanner can actually, that has more bits of precision than the scanner can actually encode. And so adding more just wastes space. But those data types may not have exactly the value range that you want to encode. These values that come off the scanner should have something approximating a physical interpretation. So say a bold series we think has plausibly values from around 500 to 2000, and we want to encode it into a 16-bit integer, which has values from 0 to 65,535. So we can calculate a slope that allows us to utilize those 16 bits of precision, and that's what I'm doing here. And this is just demonstrative here. So I'm going to say, here's my range, here's my number of bits, and my slope is going to be the actual range divided by the number of bits, and the intercept is just going to be the lower bound of that range. So here it's 0.02-ish and 500 intercept, which makes sense. And so we might have an on-disk value of 130, and that will encode a value in real terms of around 503. Okay, there is a question. What is the use case for NiBabel for these functions? Is it for those creating software or needed for those who use routine analysis or loading data for machine learning process? Okay, maybe I can discuss that a little bit later after this, just to not lose the thread, but I will get back to that. That's a good question. Okay, so just to demonstrate this, we'll create an image from some random values and we'll set our plausible range. So we're going to create a random uniform. We'll get 24 values from 500 to 2000. So similar to earlier, except for instead of getting sequential numbers, we're going to get random numbers. And when we look at our images, we get this floating point data. So in this case, it turned out to be 840-ish for that one. And if we save it as a unit 16, so we set the data dtype to unit 16, and then we just save it. We don't have to do anything else. Then we load it up and we get the data, and our values are pretty close, but not quite. So we're seeing a 0.02 or some such. Well, we're seeing a maximum difference of 0.0098. And that's going to be about half of the slope that gets encoded. And for most cases, that is as much precision as you actually have. So it's a question of how much do you care about not modifying the data versus how much do you believe those extra bits of precision. If you're operating as in float 32s or float 64s, there isn't enough information coming off of the scanner for you to really believe anything but, say, the first 12, maybe 16 bits. So this can be a very useful place to save space without losing interpretability. Okay, so what's going on? So the array proxy is where the scaling factors are kept track of. So this int16 image, if you look at the data object, it has slope and intercept encoded in there. And so these are pretty close to what we calculated as the likely slope and intercept. It looks like I just so happen to have my lowest value was 600.53 as opposed to 500. It's fine. And then we can use data object.getUnscaled to get the information directly off of the data or off of the disk. So here we're not applying any changes. And so we have these purely integer values, and you're going to see 0 because that's the lowest value, and 665,535 in there somewhere. And everything else is just scaled between those as close as possible to its original value. So scaling is done when we access the whole data, or if we do it by slice. And whether so if we're converting to a NumPy array, it will do this conversion for you. You don't have to use getFdata to ensure that that your values are correct. The only way to get incorrect values is to use getUnscaled. And if you're doing that, I really hope you know what you're doing. Slicing images, same thing. If you take the first value, it's exactly this. And so what we're doing is guaranteeing that we have the intended value, but the type can vary based on the on-disk type and the values of the scaling factors, which is part of what justifies the getFdata interface. Previously, what we gave you was equivalent to this as any array. And so that if I had ints and there was no scaling, I would get ints back. But if there was scaling, suddenly I'd be getting floats back. And so if I write software that works on my data and then you give me data that's encoded slightly differently, sometimes I get confusing results, and it's a little bit subtle how you got there. So getFdata is designed to be a fail-safe approach, and then anything else, when you start playing with the data object, this is sort of expert mode. Please know what you're doing. Yes, so this is a demonstration of this. So our proxy image originally had the data type of int64, but the data type coming out of the scaled image is float 64. Okay, and again, get data sweeps these details under the rug. Okay, so I think there's probably some questions, but I think we should be on to the don't panic slide. So let me just say this and then I'll get to the questions. So here we are, and I appreciate you sticking with this. This is definitely more for the expert users, but I hope that they give some context for people who might have to read some code that uses these structures, or if they run into things, they'll vaguely remember, oh yeah, this data object thing might be what I need, and then go find our documentation and see and learn more about it. So if I can summarize it in 3 points, use get fdata, and this will fetch all the data and it will always be a float. Data objects exist if you only want some of the data, possibly for memory reasons, or you need to control the data type better. And both methods will transparently scale data when needed. So neither should give you incorrect data. It's just a matter of preference. Okay, now let's look at questions. So just to clarify, does working with array proxies speed up the processing? Often it does. And so the most common way that you'll want to use them is the slicing. So if you only need to get a subset of your data, the slicing will save you both time and memory, so that you're not wasting time loading and representing data that you have no intention of working with. Okay, and then what is is there an important distinction between get fdata and get data? Yes, get data is deprecated. For the reason that I said previously, which was that it has an unpredictable data type. It's perfectly predictable if you know everything about the header, but if you're writing a tool, usually what you want is to work with the data as it's intended to be seen, and you aren't particularly concerned with the data type. And so, for instance, you might write your code based on the assumption that you're going to get floating point data, and then you get an image back that for whatever reason is interpreted as an int, and that can just cause problems. So get fdata is there to be sort of fail-safe. Okay, what is the precision difference in scaling factors? Is this precision difference in scaling factor something to worry about, or get fdata takes care of it all? Precision difference and scaling factors. So the difference that you get, so when you say cast a float 32 to an int 16 and add scaling factors, you will lose precision, because I think float 32 has 23 bits of precision and the int 16 has obviously 16 bits of precision. Now, the question is, do you believe those extra 7 bits of precision? When you get data off the scanner, it doesn't have 23 bits of precision. So even though you performed some mathematical operation and ended up with some values in those final bits, doesn't necessarily mean that they should be interpreted. It's like, basically, if you go back to significant figures discussions from like high school chemistry, you might get extra values in your result, but sometimes you just have to truncate them. Now, you don't have to really, floating points will save perfectly fine, but I would say in most cases you don't care and shouldn't trust, and so any precision that gets lopped off should be considered not problematic. But this is obviously going to depend on use case, so you also shouldn't take that as a 100% all the time answer. Okay, okay, so now might be a decent time to discuss what's the use case for NiBabel or for these functions for those creating software. So yeah, I mean, NiBabel is very useful for creating software if you're writing in Python to make a tool. But I think it's also really useful. I use it all the time. I just open up a Python terminal or a Python shell, and we'll just load a file and look at it to figure out what I'm doing. And so often you'll open it up, look at the file, end up writing a little bit of code to do what you want, and then you'll turn that into a function. And whether that becomes part of your analysis package or pre-processing, or if you turn that into something that you want to share with others, it's kind of up to you. I think NiBabel gives a good interface for both modes of operation. So hopefully that answers your question. Okay. So that was all getting pretty deep. And so I'd like to share something that's at least a little more pleasant to work with, which is the array slicer, or no, the image slicer. So when we pull this data object out, we're losing, we have the potential to decouple it from the affine and the header. And so sometimes the things we want to do aren't actually that hard. Sometimes it's easiest, we really just want to take a slice out of an image and have that image right back. And when we do that, we also want to preserve the spatial interpretation of the image. So let's look at the T1 weighted image from earlier. Here's what it looks like in ortho view. Notice that the crosshair is indicating the origin, shows us in the medial parietal lobe. So we can crop the image. We can just say there is a lot of black empty space around the head. So I'm going to crop some from the sides and some from and I'm going to crop some of the neck and the space above the head out. And I just use it accessing this dot slicer object inside the image. So we're not slicing the image directly. We're slicing an object that handles some of these things, but it's conveniently provided as the dot slicer property. And so now if we run orthoview, notice the crosshair is still in the same location and we've just changed the size. And so what's changed by the affine, we've changed the translation because we've cut some information from the front of a couple of the axes. And so the slicer object will do that automatically for you because it's a pretty simple linear algebra operation to do. It's just, it's fiddly if you have to rethink about how to do it every time. So you can also downsample an image, which, yeah, I will talk more about. So the really cheap thing to do, if you just say this image is too big, but I still want to look at it. And so I might take every fourth voxel. And so I'll call this cheap downsampling. So if we look at the zooms, those get scaled automatically. So we've gone from 1 to 1.3 millimeter zooms to now 4 millimeter and 5.2 millimeter. And if you look at this, you can see some pretty strong aliasing, which is this blockiness around the edges, which is just an artifact of downsampling in this way. So this is a bad way of doing things because if you're not familiar with aliasing, when you downsample something, higher frequency values or higher frequency components get aliased as lower frequency components. So it looks blockier than the data actually is. So the way we can get around this is we can very quickly write a blurring blurring tool to just give me back the same image, and I'm going to apply a Gaussian filter with a given sigma, and I'll just pass the same image affine and header back. And so I'm doing this in the original image, and then I will end up slicing that. So I blur it. Since I'm going to downsample it by 4, I'll use a 1.5 voxel sigma, and now I can see that this image looks a lot smoother. Those artifacts have been largely taken care of. So this is not necessarily the greatest way to do things, but as far as just a quick and dirty tool to get you through something, this is here. The other thing that we might want to do, and I think this is a much more common use actually than downsampling, I'd say cropping is probably the most common thing I've seen people want to do this for. The other most common thing is I want to take a subset of time points within the image. So for spatial or for for spatial dimensions, you're actually not allowed to take just one value because that changes the shape, or that changes the dimensions. And I can talk more about that if needed. But for non-spatial dimensions, we're perfectly happy to lose those. So if I slice, say, the first 5 slices off the last index of a bold series, I get a 64 by 64 by 630 by 5 image. And so remember, we started with 184 volumes. We now have 5 volumes. All of the zooms are the same. We haven't changed anything about that. Still have a 2.5 second TR. Now, if I take just the first image, then I end up losing, I lose the TR because there's no longer a temporal separation between one volume and the next because I only have one volume. And we can just verify that when we fetch the data from this image, from this sliced image, it is identical to the data from if we just slice the data object. If you are going to downsample temporally, then you should also know that that there's aliasing issues in the temporal domain as well. Okay, so I think now is probably a good time to take questions. Since we took a break a little while ago, I might skip this one that I intended. Okay, so there was one more. Will the scaling also be accessible to other software? For example, if I open the slice nifty in AFNI for further analysis. Yes, AFNI knows how to interpret nifties. So NiBabel generates valid nifty files. So any software that reads valid nifty files will interpret them the same way. There may be some cases where people don't do it correctly, but I think AFNI was one of the groups that was formed to define the nifty standard. So I think they're usually pretty good about it. I'm not going to get into it today, but there are definitely some weirdnesses in how people interpret affine matrices in nifty. That's because there's three ways of defining an affine matrix. Okay. And Ariel, just so you know, I think I did answer this. Does working with array proxies speed up things? Okay, so let's go ahead and move on, unless people desperately need a break. If you desperately need a break, go ahead and just put that in the Q&A and we can take another 5 minutes, I guess. But so now we're outside of spatial images, and so thank you for sitting with me for all of that. That ended up being over an hour, and I expected that to be about half. So I'm going to try to go quickly through this, so I might skip a little bits. Surface images you're going to hear more about later, so I'm going to be quick. But basically the idea is you get your data as three dimensions, but you might want to think about some of the structures, such as the cortical sheet, as a 2D surface structure. And now so that the values on the surface you would consider them close if they're along the surface, not necessarily if they're close by volume. So like a good example is, two sides of a sulcus might have a long distance between them, neuronally, because the information has to spread by neural tissue. But if they're pushed up against each other, you might get a blob that looks much as if the activation in but one is similar to activation in another. So how do we talk about surfaces then? The only way to do it really is you need some kind of surface mesh. And the mesh is vertices and faces, and the vertices are just coordinates in world space, and faces is a tuple of 3 indices into the coordinate list. So I can say so I've got a bunch of vertices, and I'm going to pick out 3 of them next to each other, find out what their indices are, and throw them into this faces list, and that will say this is a triangle in this mesh. Okay, so unlike spatial images, these components are frequently kept in separate files, and this is largely for convenience and historical reasons. It's difficult to get all this information in one file, which means that your geometric information, the way you interpret data, is no longer packed right in with the data itself. And we don't currently have something like the spatial image API. Okay, what's the difference between a vertex and a voxel? A vertex is a point in space. A voxel is a point in space that has spatial extent, a 3D spatial extent. And the useful thing about voxels is if you look in any direction from them in the data array, you find something that's close to you. That's not necessarily true in vertices. There's no good way to tile a triangular mesh such that 2 points are, the closer the 2 points are in space, the closer they are in the data matrix. There's just no way to do that that will be true for the entire space. Okay, so yeah, we don't have a common interface for this, so we have separate methods for dealing with whether you get your information from Gifty or FreeSurfer, and I don't think we currently support any other surface formats, so if you like those, you should definitely get involved, and we can add support for these. So for FreeSurfer, they have pretty simple file formats, but they have a somewhat complicated directory structure that gives some of the interpretation to these file formats. Gifty as a more of an interchange format where I can expect to just send you a blob of Gifties and not an entire directory structure. So Gifty has to have a lot more of that metadata directly inside that file, and it's an XML file. Okay, so let's just try to get a handle on what these things look like. I'm going to try to rush through a little bit. So if I want to read a FreeSurfer surface, like the Peel surface on the left hand or the left hemisphere, I will use NiBabel FreeSurfer read geometry, and I can also fetch the metadata optionally. So I'm going to get the vertices, the faces, the metadata. So the first couple vertices you see are in millimeters, right, anterior, and superior of some centroid. And then the faces 0, 1, 3. So the first face is these first, the 3 of the first 4 vertices. And then we have other information. So there is some affine information here that can be useful. It tells you what file you originally got the data from, etc. So NiBabel doesn't have a viewer for surfaces, but NiLearn does. So if you just use NiLearn plotting plotsurf, you just pass it vertices and faces. So it's basic in the same way that you get it out from FreeSurfer read geometry. Okay. So same thing, we can do the same thing with Gifty. Here is a file that was actually converted from the other one. So basically the data is the same. So if we load that here, because of, for other historical reasons, Gifty is loadable through the normal NiBabel.load interface, and we can look at the file level metadata, which is very minimal. Instead, what we have is data arrays, which we fetch with get arrays from intent. Intents are nifty codes defined in the nifty world. Gifty is part of this family of formats that let you say add something more to the interpretation of the data than just the spatial information. So if we want the coordinates, we would say the point set, which is the nifty intent. And if we want the faces, we would say triangle. And because a Gifty can include multiple, what you get back is a list. So we're just taking the first one of these. And so here's where the metadata that we expected, that we saw in the whole file originally. So now most of the metadata is associated with a point set, which makes sense because these are the actual values that have right, anterior, superior interpretation. The triangles don't have that information. All they really define is a surface mesh. Okay, so the actual values are stored as the .data attribute. So if we want to get our equivalent Gifty vertices and Gifty faces, we would say we would take the data array .data and the data array .data, and so we get the same things back. Note there is a slight difference here in the coordinates, and that's for kind of a subtle reason that I'm not sure is worth going into at this point. But the faces will all be identical. Okay, so now, yeah, so that wasn't really the most fun way to get this data. So last year at Neurohackademy, we actually had somebody thinking about what's a better way to get the data out. And really, we want to get to the NumPy arrays as quickly as possible. And so this alternative method was developed, and it's just called ag data, for aggregate the data. And you can pass it one or more intents, and you'll get back a tuple similar to what, based on what you put in. So we'd say gift the vertices is just the point set, or aggregate the point sets into a vertices array, aggregate the triangles into a faces array. And so now we get this data right back. Okay, so what do we have? Okay, I think I've answered that question. Okay, so for data sampled at the surface, this is what we actually care about most of the time, not necessarily the geometry. So if we are looking in the free surfer world, there are a few different types of data that can be sampled at the surface. You might get a morphometry data, such as curvature. You might get annotations, which are labels. And then you can also get data that's just in an MGH file. And so this is if we can look at the shape of them, all of them have the same shape as our coordinate array, but the MGH file is a 3D image. It's just the first image, or the first dimension, there we go, is all of the, is where all the information is actually stored. And so we can plot any of these onto the surfaces. So somebody was asking earlier about making sure you can plot in the notebook. One thing that I had to do when doing subplots was add this projection 3D keyword. And so these got quite small. I wonder if I can make them bigger without making them go off the screen. Not ideal. Okay, well, hopefully you can look at it more closely on your version of the notebook. And so either way, the curvature is space. The labels are integer values, so they each, so you get much more discrete looking things. And then this is white gray, the percentage each vertex has of containing white or gray matter. And we can also get GIFTY data. So I have a old series that's been sampled to the left hemisphere of the FS average 5 surface in the data directory. So we can load that up with NiBabel.load. And each time point is an individual data array with nifty intent time series. So if we want to aggregate that, we say aggregate data time series. And the nice thing about this is we get it all in one array. If you look at it directly in the image, you have 240 separate data arrays that you have to concatenate yourself. So we can quickly plot the mean bold signal. Here, we're going to grab the FS average 5 inflated surface for visualization. And we'll take the mean of the data over the first axis to make sure we only are trying to plot one thing. Okay, again, a lot of things. So basically, for various reasons, surfaces are multi-file problem, and they're kind of cumbersome to deal with. So the data structures you're going to see pretty much wherever you get your surfaces, but the arrangement can vary based on whether somebody's coming from a particular software tool or is writing things in GIFTYs for portability. So if you're working with free surfer files, you need to learn to traverse the directory and identify the file types, and then you have very simple loading functions that will give you back sensible objects. With GIFTY, you need to load the file and then kind of inspect what's going on inside it. Hopefully next year we'll have a better way of dealing with that, but right now that's the state of things in NiBabel. So is there one more question? No. Okay, so SIFTY2. SIFTY2 is a mess, and I am rapidly running out of time. Sorry, SIFTY2 is fine. I didn't mean to say it was a mess, but it's, so what it is they've taken a nifty2 file and said, we want to talk about voxels and vertices at the same time. So we want to take all vertices from the left hemisphere, all the vertices from the right hemisphere, and all of the voxels from areas that aren't on the cortex, and put them in one long dimension. And this image over here gives you a sense of how that works. And then we can create, say, a time series that's, they call these gray ordinates, which means it's part of gray matter. And then you can have a gray ordinate array per time point. You can also, now that we're starting to define axes that aren't purely spatial or temporal, as standard nifties are, we could take that and say, we'll make two of these axes gray ordinates. And now we can say, here's a connectivity value between these axes. Or we might have, those are brain models. And then you also have parcels. So instead of talking about an individual voxel or vertex, you might get a group of them to talk about an ROI. And then along whatever other dimensions, you might have a scalar. So basically a particular value that you can just, a way of interpreting a value along that extra dimension. You can have labels. So I'm not sure I've actually seen what that looks like, but a way of, I guess, probably this is a label array here that shows these different ROIs. And then series, you can use a time series to have multiple values that have a similar interpretation. So I'm actually, for time reasons, I might skip over a lot of this. The quick thing to note is that it's a nifty2 file with an XML header structure that just defines what these axes are. And you can access it pretty directly if you want to, but we also have this axis interface. So instead of accessing something that looks an awful lot like this XML structure, you can say, oh, the first axis is a time series, the second axis is a brain model. And then what I've written up here, and I apologize for not having as much time to go into it as I intended, is a way of decomposing the SIFT2 brain model into its hemisphere, or its cortical surface and subcortical parts. So this is a function that takes a SIFT file, gives you back a volume. And there's enough information in it to create a nifty1 image that you can just plot. And so this is something I'd be happy to talk about with other places. Hopefully I've commented enough that if you're playing with SIFT2s a lot, that you can follow along and figure out what's going on there. Similarly, we can fetch the surface data using only the information inside the image. Here we have to do something a little bit more complicated to find which surface we're looking for, but in the end, we still just get out a set of values per vertex. And so we can plot those. And here, I've added a surface geometry Gifty file inside, or in the Conti69 directory in the data directory, so that you can plot these data. And so we could combine these into a decompose function that simply gets the data from the image and gets the brain model's axis out of the SIFT image, and then just returns me data arrays. Well, so in this case, the volume. So the volume is a nifty image. The surface data is just a NumPy array for both left and right. And so we can look at the shapes and we get sensible things out. 240 time points for each of these. Okay, so I'm going to very quickly through tractography. This might be useful anyway for people. So I'd actually never played with the tractography files before I started putting these slides together. So you can think of this as a way of how I went about exploring this data type. So diffusion MRI, if you're using diffusion, often what you're going to want to work with in the end is going to be these tractography files, which is a streamline is a series of points along a path. And then the tractogram might have data that's applies to the whole streamline, or it might have data that applies to each point along the path of the streamline. These images also have an affine matrix, usually relating to an associated image file rather than to the data themselves. And there's also file level metadata as we expect. So this should look fairly similar from the spatial type. So both TCK and TRK files are supported. I'm going to look at a TRK file because there's one in the testing directory that actually has a bit of information in it. So we can just look at the TRK file, see some familiar looking objects. There's an affine, there's voxel sizes. Here we've got scalar names and property names, which we're going to come to shortly. Streamlines API, so similar to when we were fetching the data affine and header, we can look at it. So the file has a tractogram affine and header. And then if we want to look at the tractogram, we can look at the streamlines, the data per point or the data per streamline. And then an alternative approach to it is we can treat the tractogram as a list of streamlines and index it directly. So I'm using the index 2 because of the three tractograms in here. Of the 3 items in this tractogram list, this one had the most things to look at. And so we can access the particular coordinates for this streamline by saying tractogram items streamline. We can look at the particular data for this streamline, and we can both look at the particular data for the points in this streamline. Okay, so if we're looking, the easiest thing to look at is the individual streamline to get a sense of what this type of data is. So if we look at the coordinates, we see clearly fake XYZ coordinates. And if we look at the streamline data, we get a dictionary with a value for each of these things. So the value for the whole streamline for color is a 1x3 array, or 3x1. No, just a length 3 array. Curvature is just a single value. Torsion is just a single value. Now we can also have colors for each of the points, and we have a fraction anisotropy for each of the points. So you can see here there's 5 points, so there's 5 colors. There's 5 FAs. Now we can look at this data. We can look at it all at once, and then we start seeing sort of odd objects like array sequences and per array dips and per array sequence dips. And these are objects that are intended to deal with the fact that these streamlines might not all have the same length. So we can't just use ND arrays, but they're still trying to provide a coherent interface. So we might say, let's see the data per streamline for mean curvature. And now instead of getting 1 value, we get 1 value per streamline. If we look at the data per point for FA, we get 1 value per streamline per, we get an array sequence back. So that's 1 value per point, but then each of the streamlines is also in this sequence. And we can also index these by integer instead of just by names. And so there's multiple ways to look at this data, and it's probably going to depend on what specific questions you want to ask. Okay, thank you all for bearing with me through all of this. I hope you managed to get something out of it, regardless of what level of familiarity you had with NiBabel coming in. So just to reiterate what we were aiming to learn. So we learned how to load and save images to and from file names and from to and from byte strings. We learned a lot about the spatial image API and spent a fair bit of time on the header, the data object, or the affine and the data object, a little bit of time on the header. The differences between array and proxy images. So arrays are exactly what you'd expect. Proxies are there to conserve memory and scale values. And get data and data object provide trade-offs between a consistent interface and some pretty fine-grained control for the programmer. And I think your familiarity is probably even more passing than I initially intended with surfaces, SIFT, and tractograms. But hopefully this slideshow will be useful as a reference in the future if you need to come back to any of these things. So thank you. And if there are any more questions, I'd be happy to take them.
All right, I think we can stop here and then we can take more questions on Slack, Neurostars, and so on. Thank you so much for the presentation, Chris, and see you soon.
Thanks. See y'all.